Okay guys, so what I'm going to do here in this video is walk through my walkthrough that I've posted. If you haven't, I have posted something that looks like this, the 3610 Lab 1 supplemental walkthrough. Since we don't have Lab, if you're watching this, hopefully this handout alone should help you. If not, hopefully this video will. So, you can ignore these, this is from previous notes. So you'll notice the first thing that I say to do is create a ports according to the handout. The handout in the lab has the ports for the entity that you want to do. Now, that's pretty straightforward to do in VHDL. You can look up examples either in the book or online how to do it. I made a mistake earlier when I sent you guys that link that has the example UART. Don't use it. It's bad code. What I wanted for that, and I wasn't clear enough, is just look at the test bench. Their test bench is good. But until you're at the test bench, don't worry about that. In fact, I've come up with a better way to explain test benches for you anyways, which is what class today was going to be about, but it's not. So, once you have your entity, we need to consider the states. And the first one is really easy. And this is why the state machine is such a useful process, is because the first state is easy, the second one is harder, and the third one is more difficult, but they kind of build on each other. So I'm going to give you the first one. Hopefully you've got there on your own, but, sorry, when I say the first one, I say the first state. And hopefully you got this one on your own because it's very simple. Now, I like doing this in a single state. Or sorry, a single process state machine, right? So I can either have a process where one process is in charge of what we'd say monitoring and updating the state, and then other process, that's process 1, and we'd have a second process, process 2, that is the state logic. Now, I don't often do it this way in VHDL. I used to do it this way in Verilog all the time, but the more of these I've been building, the less often I do the two process. And so, the single process is both monitoring, updating, and is the state logic. So, just a quick example. If I was doing the single process, I would do something like let's see how I would do this. I'm monitoring clock, right? And the syntax may not be exactly correct on some of this, but work with me. And I would probably also put in and reset, like comma reset, right? But for now, let's look at clock. And then you're going to do if rising edge of clock, then we want to do stuff, right? Every time the clock happens. If you don't have it executing only on the rising edge of the clock, things get really confused, and we don't want to do that. Okay, so we have, if the rising edge of the clock, we want to do stuff. Well, every rising edge of the clock, we're going to say state. In fact, let's give it a better name and just call it current state is assigned to next state. And that's all we really have to do. That's the monitoring. And then you'd also do something like if reset. And you would put this one first, really, because if you're doing reset, you want reset to take priority. Then you would say something like is state 0, which we know what state 0 is, so we'd actually say idle. So this is how I note my states. I usually write them in all caps. You create your states, if we look back, using a simple type declaration literally by typing out this. Type. So I'm saying receive. My receive states is a type, is, and then I explicitly define each of them. Idle, start, bit, etc. That's all you have to do to declare the types. And so now I can start using a type called stateRx who has values of idle, start bit, etc. You'll notice in the walkthrough I talk about how save data is an optional state. You really don't need it, but you can do it depending on how it fits best for your thinking. Let's see. So the idle state, that's what we're looking at here. So if we aren't doing this two process where one of them is just updating and we're doing rather than single process handling both, then you do the same kind of thing where we're going to do process on clock and reset, and then you're going to say something like if rising edge of clock. Of course, I'm not going to do anything with the reset. I'll leave that to you. I'm just going to talk about the non-reset case. So if rising edge of clock would come after the if reset, do something, else if rising edge of clock, let's do this. And what are we going to do? Well, we know from what I talked about in lecture that if this is a 1, this is a 0 on the line, high, low, right? When it's idling, it sits at 1. So we know that's what it's going to do, and when it's about to start transmitting data, it drops to 0. So we're looking for this transition. But we know it started at 1. So if, let's start with the case machine. Almost forgot case machine. Case statement, which really is our state machine. And that case is going to go into this if statement, because you only want to execute the case on each rising edge of the clock. You don't want it to be continuous, and we'll see why later. So case on, and we're just going to call this state, because we don't need the next state variable that I was dealing with up here, so I can just be state. Case on this thing called state, which is a type of states Rx. And then I do is when idle. So this is opening case, we'd end case later. When we're in idle, we want to do things. What do? Well, we watch for this edge. So if, we're just going to call this data in. That's what I'm going to call it here for abbreviation. I think it's defined as something else in your pinouts. So make sure that this is the same as the serial input. I think they may call it S data, serial data, right? And then now P data, which is the output. But so this is mapped here. This is easier for me to write. So if D in is equal to zero, right? So the ticks mean it's a bit. Then state is, well, start bit. Right? Because if it's dropped to 0, then I need to move on. Else, do nothing. Well, that's easy, right? And what's going to happen, right, is it's going to come into here. The rising edge of the clock is going to happen. State is idle. If, right, so we're hanging out in this idle. If the data is still 1, nothing happens, and on the next clock cycle, we're still in idle. If it has dropped to 0, State is now defined as start bit, and so on the next clock cycle, instead of being in idle, we're going to be inside this when, start bit, right? Because now state is start bit, because I've defined that. Reset will handle resetting state to idle, if it needs to, or when we transition to needing a new data packet, right? When we go back to idle at the end of however many states you use. So now this when start bit, it only has one goal, because we have a start bit, right? And then we have a packet of data. And we have 8 bits inside of here. And they're all equally spaced. So the only thing that start bit has to do as a state is wait until here. And then you'll notice that you can wait until the center of the first bit, take a sample, wait until the center of the second bit, take a sample, and so on and so forth. So once we're in this, done with this state, we can go into data state, which is wait and sample, wait and sample, wait and sample. But start bit just needs to wait. So it's a simpler version of the read data state, whatever you want to call that. But it needs a counter. And what we have access to a 100 megahertz clock. We know this is going to be an input. This is coming from the board. What we need to get that down to is your baud rate, whether that's 9600 baud, or I like to use the 115,200. The reason I like to use this is it simulates better, because I don't need as many main clocks in order to sample down to this level. But 115 kilobaud is still slow enough that it works really well on boards. But you can choose. You really can, as long as you do the math right. Okay, so what that means is this wait period is at your baud rate. But you need to convert from 100 megahertz. So what that means is we need a way of counting down from counting 100 megahertz for each baud and doing that conversion of 100 megahertz to baud and how that correlates to a time period wait. Now, the ways that you could do that is you could make some sort of counter VHDL block that is monitored by this case, and then you'd have something like if counter done, then go on to next state. Right? And so this logic is just watching some external counter. The other way that you can do it, and this is how I implemented it, is you can put the counter inside of start bit, and that each time the clock happens, the counter goes down 1. Right? So it initializes to some value, say it's 5,000 is the conversion rate. It's not, but say it is. Then each time one of these 100 megahertz clocks happens, it goes tick, tick, tick. This counter is counter minus 1, goes minus 1, minus 1, minus 1. And when that counter runs out, we go on to the next state. Now the thing is, if you're doing it that way, you need to initialize that countdown value. And you can either do that upon entering the state, which is complicated logic, or up here in the previous state, when I do this state goes into start bit, I could also initialize the counter. Right? Or, and there's lots of ways to do this, here, instead of counting down, I can count up. Right? And I would just compare that to some value, and if the counter reaches that value, go on to the next state. Then the initialization can be 0. In that case, you need to make sure that a reset resets that value. Because if it's not being reset every time you move in, you could have a situation where you move into that state, start counting, and then reset, go back to idle, jump into here again, but that counter has already started counting. So you need to make sure resets that value. Your data bit, which is going to come after start, which is where I'm going to leave you guys off to puzzle it out mostly on your own, the data bit has to count 2 things. It has to count both the time between bits, but also how many bits it saved. Because it does need to save data in, right? The S data. So you need to save the data, count how many you've saved, and come up with some mechanism for knowing when to move on to the save data state or the stop bit state, really. So hopefully that's enough of a clue on how to design that.